Welcome to UGC lecture series Linear Integrated Circuits. Today we are going to discuss about the comparator as a zero crossing detector and next regenerative comparator, its application and design. We have already discussed about a comparator in the previous lectures. What is a comparator? It is an operational amplifier in an open loop configuration. So, here there is no feedback from the output to the input. We will give two input signals, one to the inverting input terminal and next one to the non-inverting input terminal. Say a signal is given, alternating signal is given to inverting input terminal and V reference, a DC voltage is given to the non-inverting input terminal. And what will be the output of this operational amplifier with no feedback, which is acting as a switch, or you can say the output will be either plus V saturation or minus V saturation. That is a comparator's output. In the case of zero crossing detector, instead of a V reference DC voltage, we can give a 0 for V reference. So, here V reference is 0 and this is the circuit of a zero crossing detector. So, here the signal is given to the negative terminal and V reference, which is 0, make it as 0 to the positive terminal and output is taken. So, in this case there is no feedback. Here the supply voltage is given as plus 15 volt and minus 15 volt. This is the supply voltage given to the 7th and 4th pin of IC 741. And what is the output of this particular circuit? If it is a comparator, then the signal at the negative terminal and the positive terminal is compared, and whichever is having a higher amplitude, say Vi is greater than V reference, then Vi is given to the negative terminal. So, the output will be equal to minus V saturation, and here V saturation is nothing but the supply voltage whatever given is the V saturation voltage. Maybe it is 1 volt less than the supply voltage approximately. So, you can monitor here plus 14 volts as the output. And if Vi is less than V reference, then in this case the output. So, in that case V reference is higher, which is given to the positive terminal, and so the output will be plus V saturation. So, here, so sorry, in this case it is minus V saturation. So, you will be getting a minus 14 volts. Here it is plus 14 volts as the output. The saturation voltage is approximately 1.3 or 1.5 volts lesser than the supply voltage given to the 7th pin and 4th pin of operational amplifier. So, the output waveform can be, say this is the input waveform Vi, and consider this as V reference, because we made the V reference as 0. So, V reference is taken as a reference line here. So, whenever Vi voltage is higher than V reference, Vi is higher than V reference, the output will be a negative V saturation voltage. So, it is minus V saturation until Vi is higher, and if Vi is lesser than V reference, this case if Vi is in from this point to this point, Vi is lesser than V reference. So, V reference is greater in this case. So, it is given to positive terminal, and so the output will be plus V saturation. So, output get transited. So, this is your output of this particular circuit, zero crossing detector. And why it is called as zero crossing detector is, we have made the V reference voltage as 0. Whenever the input signal crosses this 0 voltage, the output gets transition. So, when you look at the graph, the input signal is getting it is intercepting the 0 axis at 3 points here. So, first if Vi is higher, then you have the negative V saturation at the output, and if Vi is lower than this V reference, it is a positive V saturation. So, whenever the Vi is intercepting the 0 axis, the output gets transition. So, it is called as a zero crossing detector. This is one of the example of a comparator circuit, and in the comparator circuit we will be making this V reference as some DC voltage, say V reference, positive V reference here or a negative V reference. So, according to the V reference signal and the input signal, the output will get transited, and the maximum of the output will be a plus or minus 14 volts if the supply voltage is 15. And the next one is regenerative comparator. Here we know that in the comparator there is no feedback, only the input signal and the reference signal is given to inverting and non-inverting terminal respectively. And if the signal is given to the inverting terminal, then it is a inverting comparator. If it is given to the non-inverting terminal, it is a non-inverting comparator. Now, it is if we are going to see about the regenerative comparator here. So, in this case, we will be giving some voltage from the output to the input. Say the comparator uses a positive feedback that increases the gain of the amplifier. In the comparator circuit, this offers two advantages. The high gain causes op-amp's output to switch very quickly from one state to another, and the second one is use of positive feedback gives the circuit hysteresis. We will see what is it. So, this is the circuit of the Schmitt trigger, or you can say this is a regenerative comparator. The other name of the regenerative comparator is Schmitt trigger. So, look at the circuit, the signal Vi is given to the negative terminal here. So, in this case the comparator is used as a inverting comparator because the signal is given to the negative terminal, and say normally we will be giving V reference to the positive terminal. Here some of the output voltage is fed back to the positive terminal input positive terminal of the operational amplifier through two potential dividers, say R2 and R1. So, this is now the V reference voltage, and it is some of the output fed back to the input of operational amplifier. So, because of this positive feedback, why it is called as positive feedback is the output is given to the positive terminal of op-amp. So, it is a positive feedback. If positive feedback is given, then the gain is increased. If the gain is increased, then for the input voltage, whenever it crosses the V reference voltage, then the output will be transited instantaneously, for the input exceeds the limits present at the positive terminal. So, and because of this positive feedback, you will this circuit will have hysteresis also. We will see deeply the hysteresis. What is hysteresis now? And why it is called as a regenerative comparator is, since the feedback is given to the positive terminal, the output will be regenerated again and again, and so it is known as a regenerative comparator. The major application of this comparator is to overcome the noise voltage, which reduce the problem with the zero crossing detector. It converts the analog signal to the digital signal. So, this comparator is going to convert this analog signal, say this is a sine wave, as a digital signal, say it is going to be a square wave at its output. So, how this regenerative comparator is going to convert this AC signal, a sine waveform, into a DC signal, or you can say a square waveform. So, we know that the function of the comparator, the magnitude of the input of two voltages present at negative and positive terminals are going to compare, and if the input voltage at negative terminal is higher, then the output will be a negative V saturation, and if the input voltage present at the positive terminal is higher, then the output will be a positive V saturation. This is the function of the comparator. The magnitude of the voltages present at the input terminals are compared, and based on the magnitude, the output will be either a positive V saturation or a negative V saturation. And now what happens if the feedback is given? Again the same, the two input voltages are compared and the output will be based on whichever is higher, which in whatever the input voltage is higher, the output will get the transition. So, now we have to calculate what is the output at positive terminal when the output of the comparator, regenerative comparator, is V saturation, and what is the voltage present at the positive terminal when the output of the regenerative comparator is negative V saturation. And here in some case the reference voltage will also be given. So, we will consider a reference voltage is given for analysis. So, instead of a ground here, we will consider a reference voltage here. Say there is a reference voltage, some DC voltage, and here this is the output voltage. It is either a plus V saturation or minus V saturation. So, now consider the voltage at the output of the comparator is plus V saturation. I am redrawing the circuit again, the regenerative comparator circuit again here. So, to the negative terminal we are giving the AC signal through the resistance R3, this is Vi, and to the positive terminal we are giving the output voltage, and which is divided here through the resistors R1, R2. Here V reference is given, and this is the output voltage either plus or minus V saturation. So, this is the circuit of regenerative comparator. Now, we have to calculate the voltage at positive terminal when the input is plus V saturation and again when the input is minus V saturation. Consider the output is plus V saturation and calculate the voltage here. If the output is plus V saturation, then we say that the voltage at the positive terminal as VUT, that is the upper threshold voltage. So, this upper threshold voltage is calculated using the superposition theorem. Since we have two voltages present at the output of operational amplifier and one end of the resistor R2 has V reference. So, these two voltages are applied here, and from the part of these two voltages will be the voltage at the positive terminal, say it is VUT. Once we know what is superposition theorem, make one of the voltage is equal to 0 and the remaining, keep the remaining voltage in the circuit, calculate what is VUT. So, for the first case, take V saturation in the circuit and keep V reference 0. In that case, what is the voltage fed back to the positive terminal is, keep V reference 0. So, in that case VUT1 will be equal to the voltage across R2 will be the voltage present at positive terminal. So, VUT1. So, across R2 you have to calculate, for this you have to use the potential divider rule. So, V saturation into R2 divided by R1 plus R2. So, we have to calculate the voltage across this R2, since the voltage across this R2 is the voltage at the positive terminal when V reference is equal to 0 and if V saturation is considered in this case. So, it is represented as VUT, VUT1, and for VUT2, consider V reference is given, and V saturation is 0. In this case, the voltage across this R1 will be the voltage present at the positive terminal of a comparator. Now, by using potential divider rule, this VUT2 is calculated as V reference, this is the voltage given to the circuit, V reference into the voltage across this R1 we have to calculate. So, into R1 divided by R1 plus R2. So, this is the potential divider rule. So, now we have to add VUT1, add VUT1 and VUT2. So, you will be getting V saturation R2 divided by R1 plus R2 plus V reference R1 divided by R1 plus R2. So, this is the upper threshold voltage when the V output, that is the output of the comparator, is plus V saturation. If the output is plus V saturation, what happens if the output is minus V saturation? If the output of the comparator is minus V saturation, then the output, the voltage present at the positive terminal is represented as VLT. VLT is the lower threshold voltage. And again, by using the superposition theorem, we have two voltages. So, using the superposition theorem, we are going to calculate what is VLT1 and VLT2. Finally, add both the voltages to get the threshold voltage applied at the positive terminal of the operational amplifier. So, what is the difference is only the V saturation is now minus V saturation, other terms are one and the same. So, straight away I am writing VLT is equal to minus V saturation into R2 divided by R1 plus R2 plus V reference into R1 divided by R1 plus R2. So, now we have calculated the upper threshold voltage and the lower threshold voltage, and we had come across the term called hysteresis, and hysteresis is the difference between these two voltages, upper threshold voltage and lower threshold voltage. The voltage hysteresis is given as the difference between VUT and VLT, which is given by subtract VLT from VUT. So, if you subtract, what is the term remaining? The V saturation, V reference will get cancelled and you will get 2 V sat into R2 divided by R1 plus R2. So, this is the equation you will be getting when you subtract the lower threshold voltage from the upper threshold voltage. Since you have a minus term here, and when you subtract, you make this minus as plus and this V reference as minus. So, V reference term will get cancelled and now you have two V saturation terms. So, it will be added up and it is 2 V saturation into R2 by R1 plus R2. This is the hysteresis voltage, and this is one of the advantage of this regenerative comparator. You have a hysteresis produced in the circuit by introducing this threshold voltages, by introducing this V reference and V reference, by introducing a positive feedback to the positive terminal. So, when you look at the waveform of the regenerative comparator, so here this is the signal given to the negative terminal of a regenerative comparator, and the reference voltage, that is using the reference and the V saturation, we have calculated upper threshold voltage and lower threshold voltage. Assume that these are the threshold voltages which crosses the input signal. So, here VUT as well as VLT, both are positive, and this is the output voltage of the regenerative comparator. We know that the sine wave is going to convert into a square waveform or a series of pulses based on the threshold voltages present at the positive terminal of the comparator. Now, this is the AC signal. Whenever this AC signal exceeds the voltage present at the positive terminal of op amp of comparator, the output instantaneously changes its state because of the positive feedback. So, there is no delay, it gets instantaneously changed, the output is instantaneously changed because of the positive feedback given, and so the gain is increased for the regenerative comparator. If the gain is increased, then output gets transited instantaneously. Now, we have to compare the input signal and the threshold voltage. Here we consider this VUT first. So, the threshold voltage, we know that it is given to the positive terminal and Vi is given to the negative terminal. So, Vi is lesser than the threshold voltage. So, the output is positive V saturation. So, until VUT, the output is positive V saturation, since the signal is lesser than VUT, and VUT is given to the positive terminal and which is higher. So, the output gets positive V saturation. And now, the signal is compared with the VUT. For the second time, the signal is compared with VLT, because once the output is transited, or say you can say the output is plus V saturation, then the voltage present at the positive terminal will change into a next threshold voltage, say it is VLT. So, if you compare the AC signal with VUT at one time, for the next time, even though the signal crosses VUT again before VLT, for the next time you have to compare the signal with VLT, because once the output is getting transited, the voltage present at the positive terminal, say the threshold voltage will transited from VUT to VLT, again VUT to VLT. So, not the same threshold voltage will be present at the positive terminal when the output voltage is transited. So, if you compare the input signal with VUT for the first time, and for the second time you have to compare the input signal with VLT, and for the third time alternatively with VUT. So, for the first time the signal is compared with VUT, and now the signal is compared with VLT, lower threshold voltage. So, now the signal is higher than the lower threshold voltage which is given to the negative terminal. So, the output is negative V saturation until the signal is higher than the lower threshold voltage, and for the next time the signal is lesser than the upper threshold voltage up to this point. So, the upper threshold voltage is higher, and so the output will be plus V saturation, and it is the same for the remaining intersection between the input signal and the upper threshold voltage. One point we have to remember is the signal is alternatively compared with the upper threshold voltage and the lower threshold voltage in this case. Now, we will look at the hysteresis of a regenerative comparator. So, here the input voltage is compared with the upper threshold voltage. Consider the reference line is given with the input voltage. Input voltage is taken along the reference line, and this is the output voltage. along the y axis. Here this is the upper threshold voltage, this point is the upper threshold voltage. So, if the input voltage is lesser than the upper threshold voltage, then the output will be positive, and once the input voltage is higher than the upper threshold voltage, then the output will be negative V saturation. And this is reverse. For the second case, this is reverse. Again, this is the input voltage. If the input voltage is higher than the threshold voltage, here you are comparing the input voltage with the lower threshold voltage. So, if the input voltage is higher than the lower threshold voltage, then the output is negative V saturation, and once the input signal is lesser than the lower threshold voltage, the output is plus V saturation. If you combine these two waveforms, then you will have the output voltage as positive V saturation, and it is getting transited, and again it shows minus V saturation, and it is again getting transited to plus V saturation, and this difference we have calculated it as hysteresis voltage VUT minus VLT. This is one of the application of the regenerative comparator. Say consider this signal which is added up with the high frequency noise, and if you give this signal to the normal comparator, then you will have n number of zero crossings at this point. If you see, this is a zero crossing, again this is a zero crossing. Okay, so if this signal is given to a normal comparator, you will have a many transitions for every zero crossings, and if the signal is given to the regenerative comparator, because of this upper threshold and lower threshold voltage, or you can say because of the hysteresis, you will have a transitions only when these input signal is intercepted with the lower threshold voltage and the upper threshold voltage. Whenever the input signal cross the lower threshold or upper threshold voltage, then only the output gets transited. So, this is the advantage of the regenerative comparator. The design we will see in the next lecture. So, we have discussed about a zero crossing detector is given with the regenerative comparator. It is not going to produce many transitions for every zero crossing. It is only producing a transition at the output whenever the signal is exceeding the threshold voltages because of the hysteresis produced by the positive feedback, and the design part we will see it in the next lecture. These are the references. Thank you.